Hi, today we're going to talk about calorimetry. Calorimetry is a way of measuring how much heat is being transferred in a chemical reaction from one place to another. So, a simple coffee cup calorimeter that we have here has two nested styrofoam cups containing whatever solution it is. It has a thermometer here, and it has a glass stirrer, and it has a cork stopper over here, or some way to insulate it. And so, what the idea is that the reaction, when the reaction happens, we want to measure how much heat is being transferred. Now, usually inside this cup here, there's usually water in the solution. And so from the water, we can actually measure the temperature change and then calculate the amount of energy that's being either absorbed or released. And when we're saying energy is being absorbed by the system, that would be an endothermic process where the sign of the enthalpy change or the sign of the heat exchange would be positive. And then heat being evolved or released would be an exothermic reaction. Just like exit, if I go out that door, then it would be an exothermic process because heat's being released. And the sign of the heat being released would be negative in that process. And so heat would be going out of the system. And so usually, like say when you shake hands with someone else, one person's hand is warm, the other person's hand is cooler. Now, warm and cool are all relative terms. They're not absolute numbers. And so if I shake someone else's hand and their hand is colder, I feel that their hand is cold. But really, in actuality, heat is being transferred from me to them. Heat gets transferred from hot to cold. So from higher places to lower places because of the kinetic energy. So in this case, then heat's going to be transferred from whatever's hotter to whatever's colder. And now remember, hot and cold are relative terms, but the thermometer can basically measure it absolutely. And so if we take a look here, then there's another type of calorimeter besides a coffee cup calorimeter called a bomb calorimeter, and it's used to ignite a substance, and then the amount of energy that's being released or evolved is collected, and then the thermometer measures or registers how much the change in the temperature of the surrounding solution, and then the enthalpy change is calculated there. Now, how we calculate the enthalpy change of these in calorimetry is we use an equation that you may have seen before. Q equals Sm delta T, or Q equals Mc delta T. Now, over here, the Q represents the heat or the enthalpy change, and then that would be usually measured in the units joules, represented by a capital J, Joules. The M, the M is the mass of the substance that we're taking a look at. So in both of these equations, the mass is there. And then, so the mass would be measured in grams. And so we'll put that there. That's grams. And then here, the delta T would be the change in temperature before and after of the substance that we have here. So since it's before and after, it would be final minus initial temperature. And then usually this is measured in either degrees Celsius or it could be measured in Kelvin, because those differences, remember, those scales are the same. They're just shifted over by 273. The differences should be exactly the same number in Celsius versus whatever it is in Kelvin. And then the last is S or C, which both stand for specific heat capacity. And specific heat capacity, if I rearrange the variables, I'll find that specific heat capacity equals joules per grams degrees Celsius as the units, or joules per grams Kelvin. And then that would be the same because the difference would be the same. We're going to do a little practice with it when I switch over to the whiteboard. Now, heat is an extensive property, which means it depends on the amount of substance I have. It's just like, say, if I start a fire in a campfire and I have one log and I set that on fire, it generates a certain amount of heat. Maybe it generates 10 joules of heat, which is very low. That's not really true. Now, if I took 10 logs and I put that in the campfire, I should theoretically generate 10 times that amount of heat because heat is an extensive property. It depends on how much of the substance I have. Specific heat capacity over here, the S or the C, this stays the same. It doesn't depend on how much of the substance I have. And so it would be an intensive property. Just like density, density doesn't change depending on how much I have. The density of water, whether I have a little bit of water or a lot of water at a room temperature, could be like 1 gram per milliliter. So that would also be an intensive property. So intensive properties don't change depending on their amounts. Heat is an extensive property, because it depends on the amount of substance, it changes accordingly. So heat, extensive property. Specific heat capacity, like here in this equation here that we'll practice in a moment, is an intensive property. It doesn't depend on the amount of substance that we have. Now, where we can find the specific heat capacities is in Google Classroom. I shared with you this in the reference specific heat capacity table, and it has this website here that you can take a look at, and it has all the values of substances that we have here that are common, and then their specific heat capacities at 25 degrees Celsius in joules per grams degree Celsius. And let's go ahead and practice how we can do that right now. All right, let's practice. So we're going to calculate Q like we used in the equation from before, which stands for heat or enthalpy change. And we're going to use specific heat capacity. So we're going to use, let's use Q equals MC delta T, which is the same as SM delta T, where S would stand for specific heat capacity. Now Q is the energy, and that's in joules. So that's heat or enthalpy change. This is energy, because those are all energy. And then this is the mass, and this would be in grams. This would be the specific heat capacity, and that's in joules per grams degree Celsius. And then this is the delta T, or change in temperature. And then that would be measured in degrees Celsius, or it could be in Kelvin. And so remember, this is T final minus T initial. So let's plug and chug. So we're trying to calculate the energy here, the Q, and we're given some information here. So we have 150 milliliters of water, liquid water, and we have the temperature decreases from 50.0 degrees Celsius to 25.0 degrees Celsius. So let's plug and chug this in to find out how much the energy changes. So we'll take Q equals M. We need the mass. So we have milliliters. So what we can use is we can use the density of water, since we're not given the grams. And the density of water happens to be very convenient, 1 gram per milliliter. So the milliliters will cancel out, and we'd end up with 150 grams of water. Now we can look up the specific heat capacity of liquid water on that chart. And if you look it up, it says it's 4.184 joules per grams degrees Celsius. So the substance that we have the mass of is always the substance that you'll find, or you'll look up the specific heat capacity for. And if you'll notice on the chart, water has a relatively high specific heat capacity at 4.184 joules per grams degrees Celsius. So that means that to raise the temperature of 1 gram of liquid water by 1 degree Celsius, it would require 4.184 joules, that amount of energy. So to put that in perspective, gold has a specific heat capacity of 0.129 joules per grams degree Celsius. And so for gold, like a lot of other metals, they have a relatively low specific heat capacity. It takes only 0.129 joules to raise 1 gram of gold by 1 degree Celsius. So to heat it up, it takes far less than it does for water. And we'll find out water has hydrogen bonding later on in one of the later chapters. And that's why water takes a long time to boil, like when I'm making top ramen or something else like that. And so metals have low specific heat capacity. So that's good that our skillets or frying pans are made of iron, because they also have a relatively low specific heat capacity. All right, the last thing we want to do is we want to take the final minus the initial. So our final temperature is the 25 degrees Celsius, because that's what it ended up becoming. So we'll put 25.0 degrees Celsius, because that's the final temperature, TF. And then we have the initial temperature, which is what we started off with, which was 50 degrees Celsius. And then we'll do the math. So we plug and chug. We'll do a little canceling out of the units. Grams cancel out. And then the degree Celsius, this is negative 25 degrees Celsius, because that's 25 minus 50. And so the degree Celsius will cancel out. And then with the calculator, let's plug and chug it into the calculator. And then we'd end up with a negative 15,690 and then joules. And then the negative is important, and I'll tell you in a sec, just like we mentioned before. Now sig figs, this was 25.0, so that's 3 sig figs. This is a given amount, so this is infinite, and this is 3 sig figs. So We would want to round to the hundreds place. So our final answer would be negative 15,700 joules. Now, the negative is important because the negative tells us that heat is being released from the system. And so this is an exothermic process because the sign that's negative tells us that heat is being released from the system. So it's exothermic. And it should make sense because if the temperature decreases from 50.0 degrees Celsius to 25.0 degrees Celsius, that means that energy had to be taken out of the system. And this is the same principle when we're freezing water to make ice cubes. We have to take energy out of the system. And so that would be an exothermic process. So don't forget, plug and chug. So identify the variables, plug and chug them in, look up the value of the specific heat capacity based on the mass, the substance that you have here. You find that, and then do the math. And then don't forget, if the sign is negative, that means that heat is being released or energy is being released from the system. So it's exothermic. If the sign is positive, it would be an endothermic process. Now, we can also do the opposite, where if I gave you the energy and I gave you the temperatures, you could solve for the third variable, the mass, or vice versa. If I gave you the final temperature, but not the initial temperature, but I gave you the mass and I gave you the energy and you knew the substance, you could solve for the unknown variable. So this is what we do with specific heat capacity and the calculations involving stuff like calorimetry or energy change.